We're going to find the center of mass of a solid. The first thing we want to do is visualize the solid and get an idea of what it is we're working on here. So it's the center of mass of a solid with a constant density. So that's nice. We've got a constant density. That'll make things a little bit easier. And bounded by this collection of stuff here. What could that possibly look like? Let's start breaking it down. So in the xz plane, we have x equals z, so that's a line in the xz plane. In the xy plane, we have x equals y squared, which is a parabola that opens to the right. And we have x equals 1 in both. So x equals 1, x equals 1. Z equals 0 is the horizontal axis on the picture to the left. So that doesn't give us a three-dimensional shape, but it gives us the ingredients we need to be able to draw the three-dimensional shape. So let's see. On the xy plane, we have our parabola opening on the x direction there. What do we have for xz, right? This is z and this is x. So for xz, it's this diagonal line turned into a plane. So imagine this parabola that I've drawn right here. Imagine that going up and down forever along the z-axis. It's a cylinder in the z-axis, but it's cut diagonally by this plane. What does that end up looking like? That ends up giving us a wedge shape. I didn't draw perfectly, but I hope we get the idea. It's a three-dimensional structure. It's this parabola. The parabola would go up and down forever, but we're limited by the z equals 0, the xy plane below, and z equals x, this diagonal plane slice up above. So that's what we've got. It is a wedge, and we want to find the center of mass of this thing. So we've got our x, y, z axes. We want to find the center of mass. The first thing that I'm going to say is that the center of mass, the y-coordinate for the center of mass is 0 by symmetry. And this is because the density is a constant. The density in this thing is just a constant. And so along the x-axis, the middle of this thing is where the y center of mass is going to be, and so that y center of mass is going to be 0 by symmetry. So that's really, really nice, actually. Now, for the other centers of mass, we actually have to do the work, and we need the mass for that. So let's use capital M for the mass. This is going to be a triple integral of the density, which is a constant, rho, and we'll go dz, dx, dy. So z, we're going from 0 down below in z up to the diagonal slicing plane, which is z equals x up above. So we go from z equals 0 below up to z equals x above. And then for the double integral that's left, the x and y integral, we're looking at the xy plane. We're looking at this picture, and we have x going from y squared on the left to x equals 1 on the right. So y squared up to 1, and y going from minus 1 below up to 1 above. Now that's our integral for the total mass. That's our triple integral for the total mass. The good news on these problems is that, oh, by the way, this integrates to 4 rho fifths, which I'm not doing the work for, but it's the power rule in every integral. We can do the power rule, and if you want to check that, you can, just for practice. We already have the y-coordinate for the center of mass. This is the mass. The x-coordinate for the center of mass is going to be a triple integral of the density times x, dz, dx, dy, and it's going to be divided by the same mass, 4 rho over 5. So there is some good news here, and the good news is that we use the same mass each time for the denominator, so we only have to do that triple integral once. The other piece of good news is that the endpoints on every integral in this problem are the same, because the region that we're integrating is the same. It's the same solid that we're working with each time. So the endpoints are the same each time. So this is, again, a power rule series of integrations, 3 integrals to do, and it turns out to be 5/7. The z center of mass, again, integral from -1 to 1, integral from x equals y squared on the left to x equals 1 on the right, integral from z equals 0 to below up to z equals x above, of z times rho dz dx dy divided by the same total mass, which is 4 rho fifths. Rows are going to cancel again. This is going to give us 5/14, and I'm not showing that work because I trust you to be able to do it if you want to be able to do it. So the overall center of mass on this problem is 5/7, 0, and 5/14. If you look at it, 5/7, 0, and 5/14, right, that gives us an x. 5/7 is more than halfway down. 5/14 is about a third of the way up in z. And there it is. That's the center of mass for this structure with a constant density. In these problems, remember that the endpoints of integration we're going to have to figure out once, and then we use that in all the integrals. In general, we have to do 4 integrals. We have to do one for the mass, one for the x-coordinate, one for the z-coordinate, one for the y-coordinate. We got away with a little bit less work this time because of the y symmetry. We want to be careful with that. We wouldn't have that y symmetry if the density depended on y, for example, or in other situations. But in this case, the density was a constant, so we know the y center of mass is going to be on the halfway, right in the middle of that thing, which is y equals 0. So there it is. That's how these are going to work in general. It comes down to our skill and ability to set up triple integrals and execute triple integrals, and then these formulas that give us the center of mass for x, y, z, and for the mass itself.